My name is Wilczek, and today I would like to talk to you about how to write bug-free audio code. But before we start, I'd like to give you a brief introduction from which standpoint I'm giving this talk. So I'm primarily a C++ audio developer for Android and Windows, and this is the application that I'm working on. It's called Music Maker Jam. As you can see, you have 8 channels, and on each channel you can assign a pre-made loop, right? And this constitutes one part. Then you can create your song out of many of such parts. You can record your voice. You can put effects on each channel. You can automate it. And you can also change the scales and a bunch of other audio features. So this is my day-to-day context, real-time audio C++. And another area in which I'm active, I'm also an educator through my blog, thewolfsound.com, and my YouTube channel, WolfSound. And I hope you're already a subscriber. And if you're not, then the Wi-Fi password is AudioDevCon. And I'm also you could say, a coach in the area of audio programming. So I help students, musicians, composers, and programmers not involved in audio to start in this field. And this leads me to the fact that I've seen the areas in which people struggle actually to come up with fully functional audio code. And that's also one of the sources of inspiration for this talk. This is a little bit of my background. So I also worked on Juice audio plugins and the game audio engine. I did research with deep learning in Python. That was my previous year's talk on. I also studied advanced digital signal processing, and I have huge interest in C++ and audio best and common practices. But please don't treat this talk that I'm talking from a position of an expert. I'm talking from a position of someone who wants to sleep well at night, knowing that their audio code really works. And that's why I'm running around and I'm asking people about various things related to bug-free audio code. And from this point, I'd like to give a big shout out to all the people who answered my question. So thank you so much. And yeah, you can benefit also from their knowledge. So this is the outline for this talk. I would like to give you some motivation why bug-free code is important for audio, then what to do to achieve it, and then how to do it. We'll talk about the baseline and 2 families of approaches that I think we can utilize. And then we'll conclude with some practical examples, some more resources, and of course, big announcement, because it wouldn't be an ADC talk without a big announcement. So why is bug-free audio code important to me? Well, one reason is that I rarely hear the question how to write correct code. I mostly hear, hey, Jan, you talked about this algorithm, right? And I implemented it, but it glitches. It doesn't work. So something is wrong with your explanation. And I also noticed that the Juice team also has a similar problem. So people reporting problems with Juice, which in fact actually is a problem with their own code. So that's actually the goal of this talk. So how to write bug-free, real-time audio code in C++ for various targets, but this can also be generalized to other programming languages and even offline contexts. So why is this important from a business perspective? Well, one thing is that if you have buggy audio code, then it highly degrades user satisfaction. And in the Android world, we have a hard currency for it, namely user reviews and app installs. So you can imagine that if there's a bug in your audio code, the user will very likely uninstall your app and also submit a negative review. And in this case, where it was before I started at this company, so someone reported that they apparently recorded a longer piece of their musical input, and some of it got lost, right? So I think it's unacceptable, and that's the main reason why we should care about avoiding bugs. But then also, when I know that I write bug-free code, then my confidence increases. And when my confidence increases, I'm more productive, I enjoy the process more. Then, if you have fewer bugs, then your QA team also has less work to do. And finally, what I noticed, that if you need to introduce a lot of hot fixes in your releases, then the team's morale significantly drops. So these are the points that's worth keeping in mind. So, okay, we want to write bug-free audio code. But then how people typically approach this. So tell me, does it sound familiar? You write some code, you compile it, and then you launch up your DAW session, you put in your plugin, and you start listening to it. And then it does something. So you either hear an effect, or you hear some different effect that you expected. Maybe you hear some glitches. You don't really know. So I believe listening is great, but it has its flaws. And above all, I find it a very slow feedback loop, right? Because you need to close your door in order to recompile your plugin. Then another approach where people try to see whether their code is correct, they reread their own code. But because you wrote this code yourself, your brain is familiar with it, and then it's very unlikely that you will find problems in it on your own. Then there is the code review process, which I highly respect. But the thing is that humans think very well in terms of structures and logical constructs, and that's what code review is great for. But we have this inherent problem with thinking about samples and on a sample level. Then there's a not very popular way of actual mathematical proof of correctness. So you can prove mathematically that your code is correct. You go line by line, and you prove that the invariants hold. But I've never seen this used in the industry. I've just seen it used in textbooks, really. And then there's QA testing. So you have ideally a QA team. You hand them your app over to them, and then they report back to you with the issues they found. But this, again, quite late in the process. And then if your QA team is not technical, it may take quite a significant time to find the actual reason for the problem. And finally, there's end user testing. When you ship your app to the users and you hope that if there's a problem, they will write you a nice bug report with all the steps to reproduce the problem, given that, of course, they not already uninstalled your app or trashed it in the Google Play Store. So these are flawed approaches, in my opinion, to writing bug-free audio code. So how to really ensure this? And I found answer in this book. I know, like, has anyone here read it? Okay, quite a few hands up. Great. I can highly recommend it. So it's not the newest read, but it nicely, so Michael Feathers nicely defines legacy code as code without unit test. And that's so true. That's so true. So whenever you write code that doesn't have unit tests, it's not tested, then it immediately becomes legacy code. But there are a few problems with writing unit tests for audio code in C++. And they're mostly related to dependency management, which is not straightforward in C++ as in other languages. So if you want to read from a file, you want to write to a file, you need third-party dependencies. The same if you want to analyze your signal in some way. For example, you want to calculate the discrete Fourier transform of it, then you need third-party dependencies. Then if you want to visualize something, you want to plot something, it's also not easy. The two approaches I know of consist either of launching a sub-process to plot something with a separate program, or to call a Python library. Then I find that in C++, there's quite a big code overhead. So if you want to express some idea, we typically need to write a little bit more code than in other languages. And if you're writing unit tests in C++, you may run into the problem of unclear compiler messages, but that's, of course, biased. So how can we fix this? Well, we can fix this by combining Python with Audio C++. And why is that? Well, Python has easy and fast package management. It's very easy to plot anything within Python. Thanks to third-party, we can leverage pre-made DSP algorithms and numerical operations. We have, of course, all the deep learning features. We have easy networking, file scripting, and it also allows us fast prototyping. Okay, so we want to use Python with C++. How can we approach this? I like to think about it in two ways. So either the Python can interact with the C++ output. So C++ generates some audio file, CSV file, so comma-separated value. And then the Python code can invoke the whole CMake build chain and then read this output and then do something with it. Or we can use C++ bindings and call C++ more directly. And I will show both approaches later on in this talk. Okay, so we know what we need. We need Python to do tests of our C++ code. And then we can distinguish two families of approaches to really test our code. So one is a comparison to a reference. So we want to reuse what's already been done. So what can be our reference that we compare against? Well, one thing is an audio file. And you can think about it even if you don't have any unit tests at all. So typically, if you're working on a plugin or an app, you have some notion of a project that the user interacts with. So what stands in your way of creating kind of a test project that you can, it's always the same, as some fixed parameters, some fixed structure, and exercises the functionalities of your program. And then you render the output of this test project to an audio file. You can check it into Git. And now every time you work, you refactor the code, you extend the code, you can re-render this test project again and compare sample-wise against the reference. And if something's wrong, then your automated pipeline will tell you, okay, something's changed that should not change from your reference. Another idea is to use someone else's implementation, right? So you want to implement certain algorithm in C++ for your purposes, but you can reuse what other people had already done, maybe in different languages. And then you compare them out, so output-wise. And we can reuse Python libraries, MATLAB, GNU Octave, or third-party libraries in C++. And here I have an example. I hope it's visible, because already I attended here today a few presentations where the code was too small to read, so I hope it's visible. So let's say you want to design a Butterworth high-pass filter. You want to have like a universal designer. You want to have a filter of any order. And in digital signal processing, a filter is uniquely defined through its transfer function. And transfer function, if you don't know what it is, don't worry. But basically, it has a numerator and a denominator. And we can verify that we got the filter that we wanted by inspecting the coefficients and checking if they are equal to what they should be equal to. And the thing is that if the filter is of order 2 of a specific cutoff frequency, then we can derive the coefficients by hand, right, on paper. And then you can just put them into this nice C++ unit test. But what if we have a higher order, like 3, right? Here it gets tricky to derive this on paper. So what I did, actually, is you can run a Python function from a pre-made library, and you can get the coefficients that there should be, and you can just paste them into your C++ unit test, right? You're testing C++ code with the output of a Python function that you trust in. Okay, but what if no one has yet implemented what you want to do? You want to design a completely novel algorithm. And when you do this, you typically have 4 tasks that you need to balance together. So one is the actual algorithm conceptually, right? With some tweaks, with some secret sauce. Then there's the implementation part. So you actually want to make sure that you're implementing the right thing. And then you want to make sure that you're implementing it correctly. So you can have, correct C++ code, which implements not the algorithm that you wanted. And finally, you typically need to integrate it into some wider code base. For example, the JUICE framework, right? And in this case, you can use Python implementation, Python prototype as the baseline. And that's what they do, for example, in the headphones manufacturing industry, right? Because implementing this on chips that go to headphones is quite expensive. You typically start with a Python prototype or MATLAB prototype. But also you can use C++ implementation that is very simple, very basic. We can call it unoptimized or inaccurate, and then compare it to a more advanced algorithm. And here, I listed the examples of how you can think about it. So if you want to have a very advanced pitch tracker, then you can use a simple zero crossings algorithm to validate it for some simple inputs. Then, if you want to have fast autocorrelation function, you want to implement it with a fast Fourier transform, you can compare its output against a very slow but easy to write time domain autocorrelation function. And then finally, if you implement a finite impulse response filter and you want to have it optimized, be it with single instruction, multiple data instructions, SIMD, or again, the fast Fourier transform, you can compare the output of the optimized code to the output of the plain, slow time domain code, which is very easy to write. And here I have an example with the prototype implementation in Python. So let's say I have this brilliant idea of a gain plugin that no one has ever done before. And I know what I'm saying. I'm sure there's not a plugin that does exactly this. So if you're not sure, this amazing new gain plugin, it takes samples and basically multiplies them by half, right? And this is my Python prototype. So how can I then move it to C++ so that I know that it's correct? Well, first what I do, I generate a reference. So I have some input, in this case, a vector of 10 ones. I apply this gain to it, run it through my prototype, and I save the output. And now I take the task of implementing this in C++. So this is all in one header. And now my question is it correct? Who's saying it's correct? Yeah. Okay, we don't know. We want it to be correct, but we don't know. So that's why we want to compare it to our Python prototype. And that's how we can do it, for example, using the CPPYY library. So with this library, we can actually include this header directly. And then we can actually call our C++ function with the input that we want. In this case, again, a vector of ones. So now we can compare our Python prototype and our C++ implementation with whichever input-output we want. I think it's very, very powerful. So this is one approach. We have a reference that we compare against. But what if we don't have any reference? What if we're implementing something that's not easily comparable to something else? Then we can truly leverage the power of our digital signal processing knowledge. So it all boils down into knowing your algorithm and which properties it has. And here I present 7 properties that are worth thinking about when we're when you're implementing our audio algorithm. So one thing is that if we know the input, we should know the output. So most audio effects have easily predictable output. And then if we know what the output should be, we can compare it sample-wise with what the output of our C++ code really is. And we can do it for 100% equality or some acceptable error. And for example, if you design, again, a Butterworth filter, then at the cutoff frequency, it should decrease. It should have a gain of -3 dB. So you can just run a sine through this filter and see if the amplitude really decreased. Another thing is if you design a pitch shifter, and you can test it to set its ratio to 2 and run through it a sine at the discrete Fourier transform bin number 1 with zero-based indexing, and then see that it really shifted to bin number 2. And here I wanted to make a slight detour because I think there is a certain effect that it's not maybe so widely known. So let's consider what happens if we calculate the discrete Fourier transform, or the FFT, as some people say, of size 120 in samples, and we do it of a signal like this. So just a sine, and 8 full periods fit into our DFT. So when we do this, we get nice peak, right? Because, well, it's a sine. Okay, but what if we feed through our DFT this signal, which looks very familiar, it's almost the same, because it has 8.5, 8.5 periods in this 128 samples. So I already hinted what will happen, but the result is quite brutal. So instead of 1 peak or 2 peaks, the energy spills on all the adjacent bins. We can somehow combat this with zero padding, which reveals the true structure of the peak, but the ripples remain. So please keep this in mind when you're analyzing the your signal in the frequency domain. Okay, so that was one approach. What's the other approach that we can take when we are writing unit tests for a DSP code? Well, we can think about it that a lot of DSP operations, they always have some inverse, right? And a great example of this is the forward Fourier transform and the inverse Fourier transform. And that's exactly what I test here. So we want to compute the fast Fourier transform and then the inverse. So we have our test signal like a unit step. We compute the fast Fourier transform and then the inverse, and then we verify that we got, again, the same input signal. So it's very, very powerful technique. Another technique that we can use to unit test our audio code is enforcing phase cancellation. So phase cancellation, for those that you don't know, is the effect that happens when we add signal and its copy, which is exactly out of phase. So in this example, we have a sign on the left, the orange samples, with the period of 10 samples. We delay it by 5, so exactly half of the period, right? And we get these blue samples, which are exactly out of phase. So now, what will happen if we add the orange samples and the blue samples? Yeah, so we'll get brown samples, that's right. So actually, yeah, after the 5th sample, like all the ones will be 0, right? So this is phase cancellation. And we can actually leverage this to our advantage. For example, in this very powerful structure, so the feed-forward comb filter, which is a building block of reverb or the flanger effect. As you can see, it consists of a direct path, which is multiplied by the B0 coefficient, and a delayed path, which is delayed by M samples and multiplied by the BM coefficient. And here is a simple unit test that we can leverage to test that we implemented it correctly. So instantiate our filter, then we generate a sign with period of 10 samples, set the delay to 5, set both coefficients to 1, then we process our signal, and then we verify that after half of the period, we get just zeros. It's a very powerful technique. Okay, then, because we have Python, so the principle number 4 is that we can inspect our system visually. So what can we inspect visually from our audio output? So if we're designing a filter, we can look at the magnitude response or the pole 0 plot, and in this case, then we can inspect the magnitude spectrum or the spectrogram. So this is a very neat example, I think, because it's a recording, it's a spectrogram of a singing voice recording. And then in blue is a state-of-the-art, you could say, pitch tracking algorithm. And in orange is a pitch tracker that I designed and implemented in C++. So this visual way instantly tells me that A, my algorithm really follows the pitch of the singing voice, and B, I'm not worse in this very straightforward sense than the baseline, than the state-of-the-art. So this is a very quick way how we can check that our algorithm does what it should. Then, what is also very nice is to use some well-established signal measures that are known in the electrical engineering field, maybe not as known in the audio programming field. So total harmonic distortion, for example, to check if you have any distortions in the signal, and if they are desired or not, we can act accordingly. And then there's a very nice measure of peak to average power ratio, which allows you to detect that when we have a recording with some background noise, we can detect whether our signal, whether there's a signal that was louder significantly than the background noise, which we used actually in our latency measurement feature. Okay, we're almost there. So principle number 6, if we have a deterministic DSP algorithm, it typically has some fixed algorithmic delay. And in this example, it's an FIR filter of order 3. So what we can do, we see that from its magnitude response, that at the Nyquist frequency, its magnitude is 0. So what we do, we feed it the Nyquist frequency, and then bam, we see that indeed it has algorithmic delay of 3 samples, 1, 2, 3, and then it is 0 as expected at the Nyquist frequency. And here's another example. So there's an implementation of the phase vocoder, which assumes that the algorithmic delay is the window size. And here, again, we process a unit step signal, so all ones, and then we check that, okay, the first samples that correspond to the algorithmic delay are 0, and the remaining ones are non-zero. And finally, the last principle, here I listed some of the helpful test signals that you can use to test your DSP algorithms. For example, a sinusoid, a unit step, so again, signal of all ones, and then a nice signal is a Farina sweep, so exponentially increasing sign. All right, so now we're at some practical examples, which means we're gonna play my favorite game, what's wrong with this code? And as a side note, it's not something I consider clean code, but that's something that you'll need a lot in the audio programming space. So what does it do? It's a fractional delay line. So we have some write head. We calculate the read head from the write head and the delay. Then we wrap around. Then we calculate the neighboring samples and then the weights of these samples. And we return it as the output of our fractional delay line. And for some reason, when we listen to it, it glitches, right? So does anyone know what's wrong with this? Yeah, I thought so. So let's write a unit test for it. So first thing, we instantiate our delay line, and then we push 4 samples into it. So with this setup, the last sample, so with the delay of 0. So with the delay of 0, we should get 4. With the delay of 1, we should get 3, etc. So we set the delay to 100, and the output is 0, right? Because 100 samples ago, well, our input was 0. And then we set the delay to 1.5. So this is exactly between these 2 samples. So the output is 2.5. We're good here. And then we set the delay to 2.3. Again, we get the correct value. And then we set the delay to 2. And what happens? We expect to get the sample 2, but for some reason, get sample of 0. Okay, so what happened? Well, if we look at this line, if read head is, integer, it's still a float, but it's integer, then the floor and the ceiling operations, they return the same value. So both weights are 0 now, so we get 0. And we can easily fix this by adding 1. Okay, so there's one example. And what's wrong with this code? This is actually taken from my Android wavetable synthesizer tutorial. And it kind of mimics the Android audio callback. So once again, what happens here? We get our block of audio samples, and then we iterate over frames. We get the sample, and then we iterate over channels, and write the output to the channels. Anyone? What's wrong with this code? Oh, yeah. Ah, perfect. Great. That's the correct answer. So, oops. So how we can test? By the way, I was not able to see it myself because I wrote this code, right? That's a typical thing. But congrats to you who saw it on the first one. So what we can do? We say that the channel count is 2. We have 100 samples per channel, some sampling rate. Then we instantiate our output data vector, instantiate the player, and then we pass it this data. We just call this function once, and then we save the output to a WAV file. This is the output of this unit test. And now we can go to Python, and we can invoke the CMake build. We can run just this test, and we can read in the output of this test, and then we can plot it. And then it's immediately obvious that, all right, we're writing to the first channel, but for some reason, we're not writing to the second channel. How is that if we have a loop? Well, exactly, instead of adding channel, we're adding channel count. So we're always writing to the same channel. And plus, we have the risk of writing over the buffer. So yeah, that's the fix. And we introduce this fix. We run the Python script again. Then we get the output in both channels. So here I listed some other safety measures that you can use. For me, particularly interesting points is that you can always, or most often, check implementation of scientific papers. So if someone proposes an algorithm, they often supply some implementation code of this method, and then you can compare against it. Another neat idea is to measure performance and see if your performance degrades over time. So with changes introduced to the code, then it may be an indication that a bug was introduced. And then also what I find interesting is that know your door. So every digital audio workstation has their own quirks, and it's quite interesting to know what they will do with your plugin. So what is the takeaway from this talk? Even if you have no unit tests whatsoever, what you can do, you can write a reference test to just render the output of your software in the current state. And then if you add new features to your software, then please use the presented DSP principles and ideally include them into your continuous integration pipeline or run them manually, and then rip off the benefits. Here are some more resources. Especially I like to plug my audio plugin template because it comes with already set up Google tests of your audio processor. And people often ask me, well, how can I learn these DSP principles, right? So it's nice that you know all the properties. We learn about the 7 approaches here. But what if I want to dig deeper? Well, I have some book recommendations on my blog. And actually, the problem with books is you typically need a lot of time to read them. They can be quite costly, and they often assume that you have that you're a student, basically, right? So you know the calculus, you know complex algebra, etc. So what I came up with is a structured learning path. So if you want to learn digital signal processing from scratch, I have an online course that teaches you just this. And this is suited for audio programming. And it doesn't assume that you know anything. Even it assumes that you don't know programming. It really explains all the concepts from ground up. If you're interested, then please head over to wolfsoundacademy.com/DSP-pro. And with the ADC23 promo code, you can get 10% off. And at this point, here's the link and the QR code to the slides and the example code. So all the examples that I had in the presentations, you can compile them, you can run them, and you can adapt them to your own code base. So feel free to do so. And if you have any questions, any doubts, then please shoot me an email at this address. So thanks a lot for attending this talk.